So continuing our trip outward through the solar system, through the planets, we want to talk about Jupiter today. And in all of these videos about the planets, I'm trying to stick to the very, very basic information that you absolutely need to know for the course. After every one of these videos, you should absolutely read the book chapter about that planet. You should absolutely watch any supplemental YouTube videos that I post and get some more of the nitty-gritty details and maybe get some of your questions answered that these videos aren't going into a whole lot of depth on. The Jovian planets, the gas giants, include Jupiter, Saturn, Uranus, Neptune. Here's Earth to scale with the Jovian planets. We talked about the differences between the terrestrial planets and the Jovian planets in a separate video. The planet Jupiter is the biggest planet in the solar system by quite a bit, the largest Jovian planet, and sort of the prototype Jovian planet. Jove, or Jovian means like Jupiter. When we look at Jupiter, we are just seeing the tops of its clouds. We're not seeing any solid surface. In fact, Jupiter doesn't exactly have a solid surface. The Jovian planets are called gas giants because they are essentially entirely made of gases until you get to the very, very center. The atmosphere of Jupiter is mostly hydrogen. Most things in the universe are mostly hydrogen, about 90% hydrogen, 10% helium, with trace amounts of other compounds like methane and ammonia, very small amounts of gases like ethane, and even a little bit of water vapor, but a fraction of a percent. In the clouds, we also find ices, ammonia ice, water ice, methane ice, sort of like tiny ice crystals high in the Earth's atmosphere. You will find in the winter, that's where snow comes from, right? So frozen vapors in the form of little tiny ice crystals, and the different gases of Jupiter's atmosphere and the different sort of trace elements in the atmosphere are what give the different colors to the clouds, as we'll see in just a minute. The temperature at the top of Jupiter's atmosphere is about 250 degrees below 0 Fahrenheit. Jupiter is about 5 times further from the sun than the Earth is, about 5 AU from the sun. Because light follows an inverse square law, 1 over r squared. If you're 5 times further away from the sun than the Earth, that means you get not 1/5 the amount of sunlight, you get 1/25 the amount of sunlight. So as we go further and further and further out into the solar system, the temperatures start getting colder and colder and colder. Here is a closer-up picture of Jupiter, I think from one of the Voyager spacecraft. This is one of its moons that looks like Io, and that black circle is the shadow of Io falling on the cloud tops. But when we look at Jupiter, we see these alternating bands of dark and light, and they correspond to essentially high pressure and low pressure systems in the Jovian atmosphere. We also see a lot of turbulence and storms that happen at the interface between high pressure and low pressure systems, just like thunderstorms happen or hurricanes even happen at the interface of a low pressure system and a high pressure system on the Earth. A hurricane, and those of us who live on the East Coast are relatively familiar with Atlantic hurricanes, are low pressure systems that come from the sea to the land, and are temporary storm systems at the interface of a low pressure system and a high pressure system. On Jupiter, the low pressure systems and high pressure systems are essentially permanent. Jupiter rotates very fast. It's much, much bigger than the Earth, but it spins around once every 10 hours or so. So the low pressure systems and high pressure systems on Jupiter are stretched all the way around the planet into these permanent features called belts and zones, and I can never remember which is which. One is high pressure, one is low pressure. When we look at the atmosphere and see these different colors of the belts and zones, what we are seeing is down to different depths in Jupiter's atmosphere. For example, when we see this orange layer, we are seeing down to a layer of clouds that are rich in ammonium hydrosulfide ices. When we see the blue color in some of these areas, like here, we are looking down even deeper into a layer where there's a lot of H2O water ice in the clouds. And so the different colors of the different clouds correspond to different depths. This is actually a graph of the temperature. The horizontal axis of this graph is temperature versus height, and as you go deeper and deeper into Jupiter's atmosphere, it gets colder. The stratosphere is actually warmer than the top of the clouds, but then once you get deeper and deeper and deeper into Jupiter's atmosphere, it gets hotter and hotter and hotter the deeper you go. we've actually sent a space probe into Jupiter's atmosphere, so we have a pretty good idea of how its temperature and pressure varies with depth. The most prominent feature on Jupiter is the Great Red Spot, which is a permanent storm system. You can think of it like a giant hurricane at the border between one of these high pressure and low pressure systems that rotates like a cyclone. It is at least 300 years old. We have known about it since the 1600s, I think. It has changed appearance over the years. For a while, it got smaller and less well defined. It was kind of the big pink spot more than the Great Red Spot, but in recent years it has gained strength again and is back. And you can look at very close-up pictures of it and see this kind of swirling turbulence, not too different from what you would see in a picture of a hurricane here on the Earth. The exploration of Jupiter, I think, is what comes next. Goes all the way back to the 1970s. We've sent our first 2 flyby missions past the planet Jupiter in 1974 and 1975. Those were the Pioneer spacecraft that have since left the solar system. In the late 1970s, we flew past Jupiter with Voyager 1 and Voyager 2. All of these missions were what we call flyby missions. They didn't stop and hang around in the Jupiter system. They flew right by and kept on going. Voyager 1 and 2 both went on to Saturn. Voyager 2 actually kept going to Uranus and Neptune and then out of the solar system entirely. In the 1990s, we launched a mission that actually stayed around Jupiter and orbited it from 1995 until 2003. That was the Galileo Mission. So a lot of our most recent scientific information about Jupiter and its moons comes from the Galileo mission from the late 1990s, early 2000s. That mission was actually, at the end of its life, deorbited into Jupiter, which is the fancy word that NASA uses for crashing into something. It actually, this was planned all along. The mission was ended by having the Galileo spacecraft actually go into the clouds of Jupiter and burn up on its way down, but taking data the whole way down into the atmosphere. We have flown a couple of spacecraft by Jupiter kind of as an afterthought. In 2000, we sent a mission to Saturn called Cassini, which we'll talk about when we talk about Saturn, that flew past Jupiter in the year 2000, took some pictures. New Horizons was actually a spacecraft going all the way to Pluto that flew past Jupiter in 2007 and took some pictures and data on the way there, even though that wasn't its primary mission. Most recently, the spacecraft that is still in orbit around Jupiter is the Juno mission. It was launched in 2011, and in 2016 it entered orbit around Jupiter. And the thing that makes Juno's mission unique is that it is on a polar orbit around Jupiter. It doesn't go around the equator. When you launch things through the solar system, they tend to go in the plane of the solar system, which means you wind up getting a lot of pictures of planets from the view of the equator. But we actually intentionally put Juno in a polar orbit around Jupiter so we could see what it looks like in the poles. It looks super cool. You can get views of these storms that are closer to the poles that you can't see as clearly from the equator. And as you get down to the polar regions, you see this really, really interesting turbulence. Here's a view of Jupiter, I think the south pole of Jupiter, showing these kind of swirling, turbulent motions of the clouds. It's actually really, really complicated, and that scientists are still working on modeling and fully understanding. So the atmosphere of Jupiter is really, really interesting, and there's lots of stuff to learn about it. And we are still getting data from the Juno mission as we speak. It's going to go for another 4, 5, 6 years. Depending on what year you're watching this. I think it's supposed to go to 2026 or so. And sometimes if a spacecraft is still working properly, those missions will be extended after that. So we still have a lot to learn from Jupiter, about Jupiter from the Juno mission. As far as what happens when you get beneath those clouds, as I said at the beginning, the Jovian planets like Jupiter and Saturn don't really have what we would think of as a solid surface. They are essentially all atmosphere. As you go deeper and deeper and deeper into Jupiter, there's a gradual transition from H2 gas, molecular hydrogen, to what we call metallic hydrogen, hydrogen where the hydrogens aren't bound together as H2. The hydrogens are just free to move around, and the state kind of gradually changes from gas to liquid to this kind of liquid metallic, very unusual state of matter that we're not really familiar with on Earth. In the center of Jupiter, we believe that there is a core that is made of rock and ice, much like a terrestrial planet. In fact, there's the Earth. By comparison, the core of Jupiter is probably around the size of Mars or the Earth. Do we know for sure that that's in there? No, we don't. But we can make guesses on what the internal structure is like from measuring the mass of Jupiter. We know how big it is. We know how dense hydrogen gas is. We know it can't be all hydrogen gas all the way through. So there's probably a center that's more dense. You could, if you wanted to, I suppose, think of that as Jupiter and think of all of this as Jupiter's atmosphere, but that's not the way we think of it. We think of Jupiter as a gaseous planet that's gas and hydrogen all the way through until you get to this little Tootsie Pop center of rock and ice. Saturn, we expect, is much the same in the center, that there's this gradual transition from a gaseous state to this liquid metallic state. As you get deeper and deeper, it sort of turns into a hydrogen slurpee, from gaseous hydrogen to this more kind of frozen liquid form of hydrogen. All of the Jovian planets have rings. The rings of Jupiter are hard to see from the Earth. This is, in fact, I'm not sure they were discovered until the Voyager spacecraft flew by. This is a picture of Jupiter taken from an angle that we cannot see from the Earth. We are closer to the sun than Jupiter. So when we look at Jupiter, we are always seeing it lit by the sun. But the Voyager spacecraft flew past Jupiter so that it can look back at Jupiter and see it backlit. And when you see Jupiter backlit, you can actually see it has these very thin rings, not at all as spectacular and as easily visible as the rings of Saturn, which you can see from the Earth with a $200 telescope. But Jupiter's rings are there. Uranus and Neptune also both have rings. So rings seem to be a very common characteristic of Jupiter-like planets. The last thing I would normally talk about now is to talk about Jupiter's moons. Jupiter has some of the most interesting moons in the solar system, including moons that might have liquid oceans under the surface, that might even have life, maybe, question mark, probably not, but it's not impossible. But I'm going to leave that discussion of the moons of Jupiter to a separate video all by itself.